Good day, Dr. and peers. Today, our team is proud to be present our enterprise-grade networking solution design and implement for the TechNova solution. This presentation details our complete network simulation, configuration, execution, and the security handling framework built entirely to client and the academic specification. To provide context, TechNova solution is an expanding multinational corporation requiring a robust data bridge between its corporation headquarters in Cyberjaya and its branch office in Penang. Our primary technical objective were to structure architecture that prevent layer 2 switching blocks, automates device addressing dynamically, establish reliable cross-site data paths, and enforce the strict endpoint security, access control, all the corporate environments. To ensure smooth delivery within our groups, responsibility were clearly divided according to our primary engineering role. As member 1, I am Edwin Teo, and I look after part 1, which covers our baseline network topology layout and foundational switch and router management plane handling. Moving into part 2, Shane takes charge of configuring our broadcast separation boundaries through the virtual LANs, multi-VLAN, trunk lines, and high availability LCP internal channel aggregation bundles. Next, Wong Wen Chong Part 3 covers our layer 3 VLAN, inter-VLAN, routing logic, and automate dynamic DHCP service across all corporate branch. Finally, Junior commands Part 4, executing our infrastructure loop protection using the spanning tree protocol alongside strict switch port security control to guard against the command LAN infrastructure attack. As seen here, in our complete production simulation workspace, our network follows the classic industry instant Cisco hierarchical design model. Rather than building a flat network, we structure a clear logical boundary that separates our core distribution routing system from our SJSS switches. This guarantees that network issues inside a single branch department remain isolated and can be easily fixed without tethering our entire corporate data plans. Look closer at our branch design. The Cyberjaya HQ utilizes a high availability multi-layer switch to process intra-site departmental traffic at hardware speeds via local SPIs. In contrast, the Penang branch use an ISL 4331H router running a router on a stick framework. So this structure breaks down a single physical interface into a virtual sub-interface, allowing us to route the traffic between the engineering, finance, and customer support teams with minimized hardware requirement. Now, let's dive straight into part 1. LAN switching design and the device handling. To building this multi-site structure, our team selects specific Cisco enterprise hardware nodes inside packet tracer to simulate a production-grade corporate landscape. In Cyberjaya, we deploy our 3560 multi-layer switch feeding 2 access switches. For the Penang branch, we expand the infrastructure to include a dedicated Penang 1 router to process inter-site traffic sitting upstream from our primary branch distribution gateway pinning router. Finally, every department across both sides is assigned exactly 2 endpoint computers, giving us 12 testing workstations in total to truly verify our logical isolation, boundaries, and dynamic IP service. Before allowing user traffic onto our network, every switch and router was handled to require to secure the administrative control plane. We standardized baseline security across all devices by mapping unique hostname, locking console line ports, and securing the privileged exit mode with strong encryption. Crucially, we disable legacy, encrypt telnet section on our virtual terminal access line, requiring secure SSH section for all the remote administrative traffic. Next, I will pass to my member.
My name is Lim Xue Shen. I will now present Part 2's VLANs, trunking, and Ether channel. In this part, we segmented the network using VLANs, enable communication between different VLANs using trunking, and improve performance and redundancy using Ether channel. First, we created 6 VLANs based on the departments given in the project scenario. Here is the VLAN table. We assign access port to the correct VLANs according to the number of employees. For example, the two IT PCs are connected to VLAN 10. Now, let me show you the verification. As you can see, all 6 VLANs are created with correct names and the access ports are properly assigned. Next, to allow multiple VLANs to travel between switches and to the router, we configure trunk links using 802.1q encapsulations. From this output, we can see that the trunk ports allow all 6 VLANs. This enables devices in different VLANs and different locations to communicate with each other. Finally, we configure Ether channel between the access layer and core layer switches. There is two main reasons for us to use the Ether channel. First is to increase the bandwidth. By building two links, we get up to 2 Gbps. Second is for redundancy. If one link fails, the other link continues to work automatically. As you can see, port channel 1 is successfully formed with LACP. Both physical ports gig 01 and gig 02 are in bundle state. This provides that Ether channels is working properly with load balancing and redundancy. To summarize, VLANs provide logical segmentation and security. Trunking allows VLAN traffic to flow across switches. Ether channel provides higher bandwidth and link redundancy. And that is all for my part. I will pass to the next presenter's part.
Hi, my name is Wong Chong. Today I want to present about my project and Proctory, intervalent VLAN routing and DSCP. So The implementation of the inter-VLAN routing in both branch at the HQ branch, the status 3560 layer 3 switch perform routing using the switch feature interface. Whereas VLAN is assigning a gateway address at the Penang branch router on the stack is implemented by configuring multiple subinterface on the router with 802.1q encryption. There's configuration along hosts from different departments at VLAN to communicate with one another while maintaining logical network segmentation. Next is the inter-VLAN routing implementation. At the HQ branch, a layer 3 switch perform routing using the SVIS from the VLAN 10, 20, and 13. At the Penang branch, router on a stack was implemented using the router subinterface as shown in the screenshot subinterface like 14, 15, and 16. Create a configure as the gateway for the engineering, finance, customer support VLAN. This allows devices in different VLAN to communicate with us other with maintaining network simulation and security. And this slide shows the verification result of the inter-VLAN routing implementation at the HQ branch. Device from the VLAN 10 successfully communicated with the device in VLAN 20 and VLAN 13 through the layer 3 switch. And at the Penang branch, the engineering department successfully communicated with the finance and customer support department towards the route on the state configuration. In addition, end-to-end connectivity between the HQ and Penang was verified through successful ping decks. Static router was configured on the layer 3 switch and router to assure the communication between all VLAN across both branch. And the last is about the DHCP implementation and verification. Um, DHCP servers were configured on the HQ cross switch and the pinning router to automatically access IP address to client device. And at HQ, the IT department received an address from the 192.168.10.0 network. And at the Penang, the engineering department received a eject from the 192.168.40.0 network. As shown in the screenshot, the client successfully automate IP address, subnet mask, default gateway, and DNS information automatically. This confirms that the DHCP service is functional correctly and support effective network management. That's all for my part. Now I'll pass to next member.
Next, I will be presenting on the part 4, loop-free secure network by using SDP, switch security, and dynamic or static routing. So first of all, spanning tree protocol is used to prevent layer 2 switching loops. The HQ core switch is configured as root bridge, and root bridge controls forwarding paths. The root ports will forward traffic towards the root bridge. We need this root bridge as the HQ core to prevent other lower priority switches from being designated as root bridge. And any designated ports will forward traffic to connected networks, and alternate ports remains blocked to prevent any loop happening. Next, we will move to the port fast and BPDU guard. First, the importance of port fast and BPDU guards is it immediately places access ports into forwarding state. It reduces host startup and the HTTP delay, and only used on end-user ports. BPDU guard will protect against unauthorized switches and disables the port if a BPDU is received. This will prevent STP manipulation and switching loops. The benefits of this is it will improve the connectivity and network security while keeping our STP topology stable. So by configuring the BPDU port guard and port fast, we use the default for both of it to configure the port fast and BPDU guard to all the access ports. This will prevent unauthorized switches from being connected and protects the spanning tree topology. Moving on to the endpoint security and MAC address attack. At layer 2, endpoints are vulnerable to attacks such as MAC spoofing, rogue devices, MAC flooding, unauthorized access. So to prevent this, there are a few security measures that could be implemented, such as VLAN segmentations by segmenting different departments into different VLAN, or port security by enabling port security on the access ports and disable any ports that are currently unused. This will allow access control between departments and also prevents any unauthorized devices from connecting to any unused ports, which can limit the attack spreads and improves our network security. So to configure switch port security, we use the range on ports that are active, and we enable the configuration switch port security. We also put a maximum of 1 to allow only 1 devices per port. And we use the MAC address sticky so that the switch will learn the MAC address dynamically without manual configuration. The violation we use is restrict. So with restrict, it will drop any unauthorized traffic while keeping the port operational without shutting it down. And then for any unused port, we will use the shutdown command to prevent users. Moving on to VLAN attack, there are few types of attacks such as DTP spoofing, rogue switching, and double tagging. So to mitigate these attacks, the end user port can be configured as static access port, and any inter-switch links port will be configured as trunk ports. And finally, the DTP negotiation will be disabled. This can secure communication between departments. So for the DHCP and ARP attacks, DHCP snooping is used to prevent rogue DHCP servers and only implemented on trusted uplink ports only. This will limit DHCP requests and prevents flooding. This can be enabled on required VLANs. The dynamic ARP inspections prevents ARP spoofing while validates ARP packets. This is also on trusted uplinks only, and it will drop any invalid ARP packets. So the benefits of this is it will prevent man-in-the-middle attack and ensure valid IP MAC mappings. So for the configuration, IP DHCP snooping is configured on global configuration, and on trusted interface, IP DHCP snooping trusts are implemented. While for any end devices access port, we use the IP DHCP snooping limit to limit it to 6 per second. And finally, we will also implement the IP DHCP snooping on VLAN 10 to 60. Furthermore, for any interswitch link, the IP ARP inspection trust will be configured. And we can check it by using the do show run command include validate to verify that the configuration was applied. And finally, we have the SDP attacks. To protect against it, we will implement port fast on access ports, and all port fast interfaces will have PPTU guards. As mentioned earlier, the HQ core switch will be configured as root bridge, and the benefits of this, it will prevent rogue switches and prevents root bridge takeover. That's all. Thank you.